And welcome back to the Electronic Experimenter's Kit, episode 12, part 2, emitter follower of bootstrapping to increase the input impedance, the way it should be done. Just before I start the video, a quick shout out for this channel's sponsor, PCBWay, your one-stop shop for all your PCB requirements, be it prototypes, assembly, flexi rigids, CNC machining, 3D printing. The instant quote is easy to use. Just put in the dimensions of your board, number of pieces, how many layers, thickness, etc. Upload your Gerbers, hit the quote now button, and you're good to go. And delivery is very fast. I've used them for a few programs. PCBWay supplied the boards for the electronics kit. So back to the video. Right. I thought I'd just start off with a little explanation of how we're going to measure the input impedance. This is effectively the input of the amplifier. This is where the capacitor is here and the biasing network is part of this and the transistor is part of that. So that's just looking into your amplifier, and that is what you would see. Z-in is the equivalent of what the signal sees looking into your amplifier. And what we do is we have like a 1 kilohertz source, if it's an audio amplifier, and we have a voltage here, and we set that to a certain thing. You could quite easily, if your amplifier will take it, just say, well, we'll make this 1 volt. So for example, we'll take it as 1 volt. Now with the wiper right up this end, there'll be no resistance through here, and so the 1 volt here will appear on the input. Now as we move the wiper in this direction, we know that the impedance here, or resistance here, is going to slowly increase. And what's going to happen is you've got a potential divider between this potentiometer and this resistance, or impedance as it is. It's not a resistor, it's an impedance. And what we're looking for is when the value of RV1 equals the value of the input impedance, then the voltage here will be exactly half of the voltage here. Now, which means you need 2 meters, because it could be that as you change this and the impedance changes, the voltage here changes. Because if your source isn't a very low impedance, then it will be seeing the input impedance the impedance it sees, which is these two, change, and that will change its value. So if you may have to have 2 meters, and you may have to keep checking this one back to 1 volt while you're adjusting it until you look for this one to be half a volt. And as soon as you reach half a volt, you take the measurement across here with your meter and measure the resistance, and that's the impedance here. So it's very simple. And when you're talking in about AC terms, then you might refer to it as being when this value has dropped by -6 dBs, because -6 dBs is a ratio of 0.5. And just to clutter up the diagram, I'll just bring in the calculations for the dBs. When V1 equals V in, when RV1 equals 0 ohms, and so equals 1 volt. V2 equals V in when RV1 equals Z in, the input impedance, so it's dropped by half, so it's 0.5 of a volt. And then of course it's just 20 log 10 V1 divided by V2, and you calculate it out and it comes out at -6.02 dBs. So if you're measuring it with a meter that shows dBs, you adjust that until it reads -6. So a little bit more information for you. I've seen folks describing this circuit as being an example of bootstrapping to increase the input impedance. But how is it trying to achieve this? If we look at the circuit, the DC resistance of the collector is 2K2, the two 1K1s in series. The AC impedance is this 1K resistor, but this 1K1 resistor is totally bypassed by this capacitor. So effectively, when at low frequencies, or at frequencies where this is virtually 0, it's out of the equation, completely bypassed for AC. So all it's really done is lowered the collector impedance, which effectively, when you take that divided by that, has lowered the gain. maybe we should build the circuit and see what it does, because what it's doing is not what bootstrapping should do. So we'll see what effect it has on the input impedance. First of all, we'll measure the input impedance without the capacitor there, and then we'll put the capacitor in place. We'll measure the input impedance again and have a look at what it does. I can guarantee it is not going to increase the input impedance by much at all. Maybe slightly, maybe a little bit, but not a lot. Not to the point of saying, hey, this is bootstrapping and this is going to affect your input impedance and make it wonderfully large. So let's go and find out. Well, this is just a quick demonstration of looking at the input impedance. Here we have the circuit. The original circuit in experiment 11 had a 2K2 resistor here. I've changed it to two resistors of 1K1 each, so the gain should be the same. But what I'm looking at is the input impedance. Now, if you want to measure the input impedance, you feed the signal in here, and well, you feed the signal into here via a resistance, this resistance decade box, or my version of one, and you measure the voltage between the input to ground. So what I've done is I've got no resistance at the moment going in, and I've set the point here to an arbitrary value over here, and you see it's resting on the plus 6 dBs. This is the dB scale, and it's resting on plus 6. So when I alter the value here, when that reads 0, which is up there, then the value here will equal the value of the input impedance. And so we'll crank it up, 1K, 2K, 3K, 4K, 4K1, there, about 4K2, maybe 4K1. So that is the input impedance-ish. It's going to be a bit different because obviously this value is going to affect the level of the oscillator going in, and if you want to do it properly, you want 2 meters so that you can keep the input voltage constant at say 1 volt, and then you adjust this until the reading here equals half a volt, and then you've got the true input impedance. But this is close enough. It's somewhere around what, 4.2K, and I think I calculated it as 4.7. Now if we add the capacitor that was shown bypassing here, if you look on certain websites, they say that you can bootstrap the input impedance by putting a capacitor across here. Well, I have that capacitor. You can't see it, it's down there. I'll zoom out in a minute to show you, and we have changed the input impedance somewhat. We've gone from 4.2 to 4.9, yet they say in their thing, oh, it makes a significant increase to the input impedance, which is rollicks. It does bugger all. Right, the circuit we're going to use to discuss the increasing of the input impedance by bootstrapping is going to be the emitter follower. It provides the functions that I want quite easily. So let's just recap on the emitter follower and some of the points to remember. Number one, it has a relatively high input impedance as a design by itself. It has a voltage gain of less than unity, so slightly less than 1. And the output signal is in phase with the input signal, which is quite important. Now we're going to look at the biasing, and we've got a simple 2 resistor bias chain, and of course we want the output somewhere around halfway, so somewhere around 4.5 volts. So if we'd picked 2 10Ks, we would have had 4.5 here and about 3.9 here. So by increasing this one to 18K, we've gone up a little bit from mid-rail to give us a little chance of being mid-rail here. Right, we'll just calculate out the voltage on the base. and here it is, simple calculation, and so that will give us 5.78 here, so about 5 volts here. So if we bring them in, so there's the kind of voltages we'll be expecting. Right, so get rid of this. Whee! Right, what do we want to think about next? Well, we need to be able to control and bootstrap the input to the base. So what we want to do is break this connection and break this connection. So what we're going to do now is we're going to take the input directly to the base, and then we're going to bring another bias resistor in. So what we're effectively doing now, we're still going to provide 5.75 volts to the base, but we've given the biasing chain some impedance, and that allows us to play with this point. So the next step is we need a capacitor. And we'll bring the capacitor in. We'll move those down below. So we'll bring the capacitor in. And what we're going to do is we're going to connect and feed some of the output signal back into the bias chain. And what's that going to achieve? Well, as we saw with the other design, and we were increasing the gain, we aim to make the AC signal on one side of the resistor exactly the same as the other. So effectively the signal here is the same as the signal there. So if we feed that back with a DC block to this side of the 10k resistor, we're now going to have exactly the same signal here as we are there. And like before, if we adjusted the gain to give us a 1 volt sine wave here, then we'd also have slightly less than a 1 volt sine wave here, and we'd have a 1 volt sine wave here. And so again, we have the same voltage either side of a resistor, and if we have the same voltage either side of a resistor, then no current can be flowing, and if no current can be flowing, then that resistor is said to be of high impedance. We say impedance because for DC it's still there, it's still a 10k ohm resistor for DC, but for our AC it has a very high impedance, and that's what we're looking for. So now what we're doing is we're isolating the impedance of these two, which of course is the 10k and the 18k in parallel. The reason that you treat them in parallel is the power supply from this point to this point is considered to be a big capacitor. So AC wise, this point is connected to that point. So those two become in parallel. And so the impedance at this point is 10k in parallel with 18k in series with 10k. So we'll just think about that for a minute. Right. If I bring this in, and we look at the impedance that we would see here without that capacitor. I brought the wrong one in. Woo! Whee! Right, if we look at the bias chain impedance seen at the base of Q1, which is like this point here, and the bias chain impedance is this is R1 in parallel with R2, as we said before, in series with R4. So we get 10k in parallel with 18, 6k 43, plus the 10k, so we effectively have 16.43k AC wise if you look in to here. Now if I whiz this away, nope. Right, so let's start looking at the impedance seen at the base of Q1 without taking the bias chain into account. then it's the HFE times the emitter resistor, or R3, and looking up the HFE for a BC847A, which is what this one is, the datasheet says we can expect anywhere from 125 to 220 as a value. Now multiplying that by the 4.7K gives us an impedance here of somewhere between 587K and just over a fraction over 1 meg. So that's the best input impedance that you're going to obtain. Could be higher if this has a HFE of higher than 220, or it could be lower if it's lower than 125. It's their guarantee is it's somewhere between them. But of course you've also got to take into account that the voltage at this point and the voltage at that point are not identical. The transistor does not provide 1-to-1 gain. It is less than 1. So there's going to be an imbalance in here. So there will be some current flowing through here, which of course means that some of this circuit, the bias, will be seen by the input. So let's go back to the board, knock up this circuit and see how close we are. First of all, we'll measure the input impedance without the capacitor in circuit, then we'll plop it in and redo the impedance and see by how much it changes. So back to the board. Right, here's a bit of a cluttered up screen. We have the scope up there showing you the signal generator output on yellow and the input here on blue. We have the Vel microvoltmeter, and that's going to be measuring the voltage at this point as well. This is my series resistance on the input, so when that has dropped by half or 6 dBs, the value on here will be the value of the input impedance. And there is the circuit, just to remind you, because I'm now going to take that away as I want to bring another meter in for a few seconds to look at the voltages. So we'll just pop that out the way. We'll bring in, sorry about the reflections, we'll bring in the voltmeter, and just for a quick one we will look at the voltage on the base. Is this a dodgy lead? Something funny with that lead. Try another one. The voltage on the base again. If I can find the hole. What is going wrong? Right, there we go. What did we calculate it at? 5.7, and we calculated it at 5.75. So quite close. So what would the voltage on the output be? 5.11, and what did we calculate it as? 5.15. So this simple circuit, much closer. Now what I'm going to do now then is I'm going to move over the bit so I can zoom in more at the bits that are important, and I'm going to adjust the input. It's a nice bit out of focus, but it's just on. You can see up there, it's just on the 6 dBs, the plus 6 dB. So it's irrelevant the voltage coming in, because it's just going to be a ratio. It's going to be dropping by the certain amount. We'll get rid of that, don't need that. So I could put the circuit back. If we pop the circuit back, there we go, we'll pop the circuit back. Right, so what we're going to do now, there's a link, you can't really see it on here, there's a link missing here. So that capacitor, the C3, is out of circuit at the moment. So I'll move it about there, you can probably see it all. So C3 is out of the circuit, so we want to adjust this until we get to that 0 dB about there. So off we go. We're going to go 1K, 2k, 3k, 4k, 5k, 6k. Not a lot happening here. 7k, 8k. What's going wrong? Ah! What a silly Billy. Put it back to 0. It's actually down here looking at the oscillator at the moment. So that's a bit silly, isn't it? That's never going to change with the input impedance. So we all make mistakes. So let's bring this round. It will get in the way now. And we clip it on the input. Meter will settle down. Right, still reading the 6 that we want. Turn that around a bit there so it's the right way up. Right, and now when we click it down, we should see the value drop. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. If I move that over, because I just want to show you that it's nearly, right, it's nearly there. 16 point, you know, it's nearly dead on the 0. So we have 16.3k, and I think we calculated it out, if I can remember. Bear with me for a second. There we go. Stuff it there. We calculated the input impedance to be 16.43. So very close. We'll just whip that back out the way again. Right, so this is just a shorting link. So we put it in. Now we go back to 0 just to make sure that we're happy. We've gone up a little bit, so we'll back it off a little bit so it's back on plus 6 dBs. Or we could actually read the voltage if you really wanted to know. It's 154 scale, so it's just over 150 millivolts. And we go again. So let's go back to 16. And as you can see there, 16k is hardly moving it. So 26k, 36k, 46, 56, 66, 76, 86, 96, 106. Yeah, do we really need to keep going? 200, 210, 226 maybe not got down one. 225k. As you can see, the impedance has gone up just by putting that capacitor in. Now the reason it hasn't gone up to like the 500k that we were hoping it would go up by is possibly by the fact that there is a voltage difference between the signal here and there. And so it's not perfectly exactly the same. It's not 1 for 1. And so there will be some current flowing through this resistor, and flowing through that resistor will be seen as an impedance for AC, and so maybe that's why we haven't got the full gain. But it just goes to show that putting the biasing, not the bootstrapping in the correct position, i.e. the output back to the bias chain to effectively remove the bias impedance from the calculations, does what we expected. And putting the bootstrap capacitor, or so-called bootstrap capacitor, across that first example of the collector load did nothing. Well, if you like this one and you enjoyed it and you'd like to subscribe, please hit the subscribe button. Hit like and hit notification for reminders, and I'll catch you on the next one.